All right, in this video, I'm going to be going over my least squares assignment project. So to begin, here is the problem statement for least squares. These are the first few parts. Question 1 asks us to derive, the entire purpose of the project is to derive the general formula of the slope and y-intercept of the least squares line, given n data points. And we are given the equation of the least squares line as y equals mx plus b. And for each data point, xi, yi, we have to show that the corresponding point directly above it or below it on the least squares line has y-coordinate b plus mxi. And we can solve this or show this very easily with this graph here. So I have an arbitrary line y equals mx plus b, as you can tell over there. And the y-intercept is here at 0b. And for a point, let's say xi, yi, a data point, we can represent the corresponding point x1, y1 on the line. And notice that since the x coordinates are the same, we have x1 equals xi. And since we have this general formula for a line, we have that y1 over here is equal to m times xi, since xi is the same as x1 plus b. And this is exactly what we were trying to show. Pretty straightforward. For question 2, we're asked to show for each of the data points xi, yi, we have to show that the square of the vertical distance from it to the point that we just found is yi minus b plus mxi, all raised to the second power. And we can see this over here in this instance. So if we have, again, we have xi, x1, y1, right here, this point on the line. We can rewrite this as x1, comma, mxi plus b. And the reason why we can do that is because from this equation over here, we simply plug in this xi value. And this I should be a subscript. I accidentally made it into a normal character. As for the squares, there's a nice visualization, but the distance between y1 and yi is simply this vertical distance, and this vertical distance is just given by the difference, which is yi minus this y value, mxi plus b. And then when we square it, we get this expression, which is what we were trying to find. For part 3, we are given this function f of b of m, this multivariable function that sums the distances of all the squares that we just got in part 2 of all the data points. And we are given the partial, and we're trying to solve what the partial derivatives are. And we are given the partial derivative we're looking for. So we're doing partial derivative with respect to b and partial derivative with respect to m. So we can go about this through our normal partial differentiation method. But before we do that, it's easier for us to expand. So we have f of b equal of m. And if we expand it out for the first couple terms and have the general nth term, helps us take the derivative much easier, the partial derivative. So it's simply the chain rule, so the 2 pops down here, and we keep everything inside the same. I just distributed this -1, so we have y1 minus b minus mx1. And remember, since we're doing the chain rule, and we're taking the derivative with respect to b, the derivative of negative b is simply -1, so the -1 pops out. And we repeat this for the second and third up to the nth term. And doing so gives us this nice expression, and we can pull out these -1s and these 2s. We can just factor them out, -2 times this entire sum. And notice this in the sum, it's basically the same expression, except the subscripts are changing. So this gives us -2 times I equals 1 up to n of yi minus b times mxi. And then since we can factor out this -1 from minus b and minus m, we get this expression, which is exactly what we were looking for. Partial derivative with respect to m is a similar approach as we just did. We have our expanded out expression. Actually, this is just the partial derivative because we again take the chain rule, except notice instead of a -1 popping out, a -1 times x1 pops out because the derivative of -m times x with respect to m is simply the negative x1 because x1 is a constant and m is the variable we're taking the partial derivative with respect to. So again, we do that for the up to the nth term. And then we again factor out -2. There's this -1 hiding in here. However, we leave the x1, x2, and up to xn the same because, we still leave it in the expression because there isn't a common term. We'll just rewrite that in our sum over here. You see this xi term. So again, -2 can stay out because summation notation, you can factor out common factors. And so similar to what we did above, we just rewrite this in this nice condensed summation notation. Okay, so for question 4, we're asked to show that the critical point equations, partial derivative of respect to b equals 0 and partial derivative of respect to m equals 0, they lead to a pair of simultaneous linear equations, and those are the equations over there. So for this, we basically take the two expressions we found earlier in step 3, this one and this one, set them both equal to 0. We'll deal with the first one. When we set this equal to 0, you notice that the -2, we can just divide that away or divide it by both sides because it's a constant that we're multiplying everything by. And -2 will not affect what the inside of this is when we're trying to find when it equals 0. So we just need to find when this inside expression equals 0. So we just get this expression, and we have another summation over here by using one of the summation rules of basically distributing the summation to the components. So gets this. And then we add this whole thing to both sides. And again, we split it up again once more. And once we do that, we notice that we have this term right here, the sum of I equals starting from I equals 1 up to n times of b. And this is simply b times n. And the reason why is because we're doing basically b plus b plus b plus b plus b n times. And if you remember from multiplication, adding n times is actually the definition of doing b times n. So that's what we get over here, and the rest is what we got over here. And that is one of the expressions we're looking for, this first expression over here. For the second one, similar approach. We have our partial derivative with respect to m. Set that equal to 0. Remember, -2 we can divide away because it's just a constant. And again, we distribute the summation to all parts of the expression. And notice I actually distributed this xi into yi and this whole thing over here. And that's how I got this whole thing to split up very nicely. And like before, I add these two expressions to both sides, and this is what our final expression or partial derivative or linear equation, I should say, is. And as you can see, that is this second one over here. Okay. For number 5, we are asked to solve the equations of part 4 for b and m, getting these two giant, basically nasty equations. Okay, so this is almost entirely just algebra, so I'll quickly go over it, but I just help me save writing time, and also for clarity, I denoted u of x as this summation starting from I equals 1 up to n of x, and then I just rewrote these partial derivatives over here, and we got these two expressions. And then basically I rearranged both equations, first starting with m. So I set, if you can see in this equation, if we move everything over, the bn to this side, divide both sides by u of xi, we get an expression for m. And then similarly, we do the same for this second equation and get this equation. And then I set this one equal to this one. So we get this big equation over here. And then I solved for b, so I distributed, move everything to one side. So here's the b term, and then added that over, divided, and we get this. And then lastly, if you notice, the signs are a little bit different between these two because I divided by -1 to match the answer that is given over here. So if you see, it's the same thing. And then take a similar approach for solving for m. We have, I just wrote this expression for m just so that I can easily see how I'm going to get to the expressions for b. So I solve both equations for b, or rearrange it for b, set them equal to each other. And again, I divided by -1 to match the answer choice. And we get m equals this nasty expression. And I believe that's all I have to say for part 5. Yeah, it's just a bunch of algebra. I may have made some mistakes, hopefully not. Okay, so for question 6, we're asked to apply the formulas of part 5 to the data points 1, 1, 2, 1, 3, 3 to check that we get the same result as in the example above. And the example above is the example they give for linear regression for these points. So again, we take our expressions from the last part, pop them down here. I didn't write the whole thing out because it would be too much of a mess. But again, I just plugged in the values for each of the parts of the expression. So n refers to the number of data points, which is in this case is 3. So for this 14, I went from I equals 1 up to 3. And for each term, I squared it and added them all up for the x component. And you should get -1/3. So you have 14 times 70 minus 72, that's -2. This is 42 minus 6, so 2 over -2 over, -2 over 6 is -1/3 for our b value. For our m value, again, just use this expression, and you should get 36 minus 30, which is 6. 42 minus 36, that's 6. So 6 over 6 is 1. I accidentally got ahead of myself. I wrote y equals -x3, x over 3 plus 1. I switched the b and m values, but the correct answer is y equals x minus 1/3. And if we go back to example 3, over here, you see it's find the least squares line for the following data points. If we look at the answer, y equals x minus 1/3. Thank you for watching. Bye.